Okay, so we only discussed the simplest type of boundary conditions. So how do we treat boundary conditions in general? So the first thing we want to learn is what if I have Poisson's equation? Let me go back. If I have Poisson's equation, I'm going to use examples to illustrate how to deal with boundary conditions. So what if I have W0 is equal to a number not equal to 0, and W1 is equal to another number that is not actually equal to 0? How do we deal with that kind of boundary conditions? Well, actually the same way, right? So basically, as we integration, what we want to focus is V is a small variation in W. So if V is a small variation in W, what is V0? If W plus the small variation V has to satisfy the same boundary condition, then what is V at 0? It has to be 0, right? What is V at 1? Also has to be 0. Because basically V plus W has to satisfy the same boundary conditions. I mean, if you think about the optimization problem, I'm solving the optimization problem. I'm minimizing the objective function under the constraints of the boundary conditions, right? So the boundary conditions here serves more like a constraint. That means when I take a small variation in the function W, the variation has to satisfy what we call the homogeneous version of the boundary condition, right? Okay, so that's what's satisfied by V. So then we are still going to be going through the same analysis. The boundary condition part, I mean, I'll just show you. So the boundary condition part is going to be using integration of parts is going to be coming up with this. This is still going to be 0, right? Okay, you ended up having the same weak form AVW plus, I mean, in this case, minus BV equal to 0. You can write plus or minus depending on how you actually define V, right? So if you can define V with a minus sign, and you can write plus. So you are going to still have the same weak form, except for the space is different. Okay, the space is here for any V within H1, the Sobolev space that is whose derivative is square integrable and the function itself is square integrable, and satisfying and V0 equal to V1 equal to 0, right? So the solution and also, okay, so let me state it fully. W satisfies this condition. Okay, this is condition 1, and condition 2 is the boundary condition. W0 equal to WL, W1 equal to WR. Does it make sense? The first condition of the weak form is that A of WV minus BV equal to 0 for any V within the Sobolev space with boundary conditions. The second condition is that W itself has to satisfy these boundary conditions. All right. So that's a very simple extension of the 0 boundary condition. It's just slightly modifying the what W has to satisfy. Actually, the condition 1 is exactly the same as the 0 boundary condition case. Just the condition 2, I just replaced it with the new boundary condition. Okay, we also encountered other types of boundary conditions. What if my derivative is fixed, right? So what if I fix dw dx to be, let's say, AL at 0 and the dw. Oh, actually, I can't really set both boundary conditions to be derivative boundary conditions, right? Otherwise, I would either have infinitely many solutions or no solutions. So let me keep my right W1 to be 0, just for simplicity for now. So how do I deal with that kind of boundary conditions? It turns out in finite element, the way to deal with the derivative boundary conditions are actually completely different from the way you deal with fixed boundary conditions. Because just like in finite difference, right? In finite difference, the way you deal with a fixed boundary condition is that you eliminate that degree of freedom. Which the equivalence here is you impose a constraint. You impose a constraint on what space you are allowed to vary V and vary W. In finite difference, the way to impose a derivative boundary condition is to actually introduce another equation at the boundary, right? So we actually have additional degree of freedom if we have a boundary condition like that. You can no longer fix the boundary grid point, but you have to now set this as additional degree of freedom. In finite element, it's a little bit analogous to that in the sense that we no longer restrict the degree of freedom. We got rid of the constraint. But what replaced the constraint is actually a little bit different. We actually have to modify the weak form. Okay, so let's see how we deal with this. We still have the equation. And we still multiply the equation with a test function, and we still integrate. And we still perform integration by parts, which gives me V times dw dx 0, 1 minus the integral of this perfectly symmetric form. This is equal to 0, right? Now the difference is that I can no longer cancel the boundary terms at both ends. Okay, I can cancel this at x equal to 1 because it's still the fixed 0 boundary condition. But I can no longer cancel it at x equal to 0. So let me write it down. At x equal to 0, I have a minus sign because this represents the value of the function at 1 minus at 0. I have minus v0 times what? dw dx at 0, right? Which I have the boundary condition for. So v0 times al times something that I already know. Okay, so let's see where this term is going to end up. Okay, so now 0 equal to that is my new equation. I have this additional term. This, I still want to write the whole thing as A of VW. Well, let's just have a minus sign here. Plus B of V equal to 0. So where does this additional term go? Should it go into A or should it go into B? B, why is that? Because it's not a function of W, right? It's only a function of V. So now my A is the same. My B is no longer the same B as before. It's actually integration of VF dx minus V at 0 times AL. Okay. So the linear form is going to be changed by the boundary condition. And this weak form is W satisfies this linear form, right? This linear form for all V within H1 and V1 equal to 0. So no longer have any constraints of V0, right? V again is a small variation of W, which is not fixed at x equal to 0 anymore. So this is condition 1. Condition 2 is w at 1 equal to 0. So in neither the weak form nor the boundary condition, x equal to 0 appears. The constraint is gone. This is what's called a natural boundary condition, because by modifying the weak form, we can see that the boundary condition is going to be naturally enforced. Okay, naturally imposed.